As we think about whether a reaction will occur or not, or more correctly, whether it's favorable or unfavorable, we think about energy, enthalpy, is heat leaving or coming in? We think about entropy, disorder, is it becoming more or less orderly? And we need a way to quantify each of those things. For reactions that are becoming more disorderly or more random while releasing heat, that reaction is definitely, from a thermodynamic sense, going to be a favorable process. But we've got some other kind of in-betweens here where it may or may not be favorable from one aspect. The concept or the calculation that puts this all together is Gibbs free energy. Gibbs free energy is a way to quantify the relationship of enthalpy, heat, to the entropy, disorder, at a certain temperature. Free energy in this sense is not the same thing as enthalpy, is not the same thing as entropy. It's energy available to do work. So without knowing too many other details of the physics of it, we really just need to think of this as, is it thermodynamically, from a heat and entropy sense, favorable? And when this is negative, right there, when this is positive, right here, our delta G comes out to negative. We have released free energy, or we have released energy that's available to do work. When I have a negative value here, negative with negative, and a positive value here, all of this becomes positive. That positive delta G, or a requirement of free energy, means that energy has to come in and do work on our system. That is thermodynamically unfavorable as a standalone process. The temperature is an important factor to this because of how it can impact our entropy. So that's why we have this equation that includes both of those. If we are doing this from a mathematical sense, we do need to pay a lot of attention to units. Our temperature has to be in Kelvin. Our enthalpy, our delta H, and our delta G are generally measured in kilojoules, but entropy is normally in joules. So you have to pay attention and do whatever conversion, either everything to joules or everything to kilojoules. But conceptually, what we'll look at a lot more here is, when is something favorable or unfavorable based upon the values that we have? When I have an exothermic reaction that increases the entropy, no matter what temperature I have, that will be favorable. When I have an endothermic reaction that decreases the randomness or becomes more orderly, no matter how hot or how cold that is, it will require an outside source of free energy to occur. These other instances, and I've tried to match them up with colors that hopefully make sense, when we plug something in up here, if this is positive, the delta G will only end up as negative if I have a big enough increase of entropy. So a large or a high temperature would make that even more likely. And as the temperature goes even higher and higher, whatever the delta S factor is becomes more of a factor, and delta G becomes more negative. For a reaction that has a negative right here on my delta H, but a negative right here, that higher temperature, negative and negative, this becomes more and more positive, making my delta G less and less negative. So this is most favorable at low temperature. With both of these charts, there's going to be a temptation to memorize this chart and that chart, but it's going to be a lot more practical to just know when and how to use this equation. We want this to be negative. What has to be true about H and S to make it always negative? What has to be true about H and S to make it never negative or positive? What has to be true in terms of temperature when those aren't true? So the other thing, and a tip that sometimes helps, especially as we're first learning this, it's when the signs of these two match, the negative and positive, that is where it is temperature dependent. When they're opposite in sign, it's either always or never favorable, but when they have the same sign, the temperature does matter. That high temperature versus low temperature depends exactly how negative and how positive our H's and our S's are. So low and high are relative terms, and we can calculate the exact values there. And the other part with this is to say, and it's a phrase I used previously, anytime I have an exothermic reaction, when that is favorable, it's because the enthalpy is driving the reaction. The enthalpy is a favorable portion to this process. Whenever we say I have a positive delta S, so this row right here, that means I have a positive change in entropy. The entropy would be driving the reaction. So I can have a system where only enthalpy drives it, where only entropy drives it, or where both of them drive it. And we want to be able to understand this mathematically, conceptually, and kind of comparatively as well.